Okay, so welcome back. So let's just get started on the design of the common source amplifier. So okay, yes, it's. So I'm supposed to take you guys through the calculation and all, but um, with the facilities I have, or is it the amenities or the infrastructure, it's not enough for me to be able to um, record my calculation as I'm doing it. So I don't have the resources, I don't have a camera for that, and yeah, so maybe I would find out if there is any app that would enable me to use my phone as camera, and that would um, be easy to interface with this recording app, that's the OBS Studio. So, but till then, I just decided to do it this way. So I did the calculation already, and all I'm just going to do is to take you guys through. I'm sorry, apologies. It's not looking that neat. So don't worry, I would upload a neater calculation, yeah, in the video description, or I may just share it with your class later. Maybe I'll just have one of your course mates rewrite this in a neat way, then yeah. But don't worry, I'm going to take you guys through the steps here. So okay, so that being said, let's just go. So as you know, yeah, so remember this what we want to design, right? So let's not forget, and we have it down here. So for your hand calculation, you need some parameters, and those are usually the model parameters. So model or process, whatever, whichever. So and a few of them are given here. You have the transconductance parameter here for the PMOS and the NMOS. So that's the mu Cox. You have the values here, 115 microampere per volt square, and for the P type it's 30 microampere per volt square. We have the threshold voltage 0.65 for NMOS and minus 0.78 for PMOS. Then we have the maybe what you call lambda, but also the channel length modulation parameter. So again, so you can see first. Okay, let me just state what I want to state first, then before I say what was coming to my mind. So here I wrote 0.24 to 0.38 approximately. So any values in that range. So how did I get all this? It can be difficult. I mean, working with the PDKs, being that whether it's Skywater or Global Foundries, being that they are based, I think it's BSIM 4.5. Yeah, BSIM. It's and the level is quite advanced. Remember, in your SPICE modeling, you have different levels. Level 1, the basic, for which the square law model of transistor works for, like better, like accurately. But as for other levels, the square law, it's not really accurate that much. It's not accurate. So but it's still good doing your calculations with your square law model. When I mean square law, I mean all these formulas you're seeing here. These formulas are based on the square law formulas. Where you want to find your GM using the square root of that. You want to find the sizing. You can see the formula, like, so it's just based on the square law. So even if it's advanced level, you using the square law for calculation still comes in handy, because as engineers we want to feel what we're trying to do, even if it will not be accurate, you get. So but at least the square law can tell us where we are, how close, to have a better picture of, okay, what things may look like, you get. So that's and for the advanced level spice model, all these parameters are not easy to get. Most times you just have to approximate, like, so that's what I did for my case. I had to do parameter extraction in my own way to get. So yeah, these are just approximate values. Yeah, after several iterations, I just picked these ones. These ones look like they are better values and all that describe those models better. So for Skywater, yeah, it's going to be different slightly. So what I'm going to do is that I would get the system of one of your course mates, so I can go through the Skywater model and do the extraction for you guys, so you'll be able to do your own calculation. Yeah, because I'm using Global Foundries, so, and I don't have the Skywater on my own PC. So yeah, then I will help you guys extract these values, but for now you're just all fine. Let's just use this and just move. Basically both of them are based on the BSIM, I think 4.5 version 4.5. So yeah, these values may be quite close, around close range. So yeah, so that's just a note on how I got these values. You always need these values for calculation and calculation. So then next I move to my specification. For every design, as engineers, right, you need to get specifications. And yeah, specifications can be tricky. Meeting specification can be tricky many times, because specifications can actually what's the word, they can collide with one another. They can two or more specifications may not coexist at the same time. Yes, so that's why working with specifications can actually be tricky. So you just need to work with the right specifications. Sometimes it's not because you as an engineer you can't do the work. Sometimes it's because the specifications are not realistic or cannot be met, you get. So but notwithstanding, specification is still the starting point. I'm just trying to emphasize how important specification is, that when you get it wrong, everything can be wrong. Also, everything about the design can be wrong. So you can see there was something I had to clean off here, because if I give that specification, that will be over specification and it will make things go wrong. So I just had to clean that off. So I'm just going to be working with two specifications, and the two specifications I have here, one, this is the output swing. So outputs, okay, so what are specifications? Specifications are those those features you desire your design to have. So when designing a common source amplifier, what do you want? Specification could be gain, yeah, the output swing, the power dissipation. Maybe you don't want your amplifier to dissipate much power, you want to just do a low power design. What else can be specification for a common source amplifier? I know maybe you guys may have not gone to frequency response, so you can get specifications too from the frequency response. Okay, how fast do you want your amplifier to be? So you're looking about the frequency. How much does it take for it to respond to input signals? You're talking about the slew rate, right? So there are so many specifications, but for being that common source amplifier, it's just a simple amplifier, it's just a basic amplifier. I'm keeping the specifications like simple. And again, another reason it's two or more specifications may not be able to coexist together, may actually collide with one another. So that's usually what we call trade-off. Yeah, trade-off. Why did I not mention that word earlier? So that's what it's called, trade-off. Sometimes if you want a specification, you need to like give up on another specification, like more or less like you not being able to eat your cake and still have it. Yeah, it happens. It happens very well. That's what it's called, trade-off. So that being said, it means when you have a lot of specifications, just get ready to trade off a lot of things, because the more you have, the more your specifications, the more collision you would have with one or more, two or more specifications. So that is, if you keep your specifications very simple, then yeah, you have it easy, you don't have too much. So that was another reason why I'm picking a simple just few specification. Number one reason, this is just a basic amplifier, so I shouldn't just try to demand too much from it. That's one. Two, the more your specifications, the more your trade-offs. So you just need to get rid of it, and that means you have to do a lot of balancing before a simple design will become a complex design. Because why? You want to, since you need this and the other one is acting wrong, you just need to balance things before your design is becoming complex. You're adding more things to your design. Maybe you're expecting to just have 3 transistors, before you know it, you already have 5 to 7 transistors. So that's why this design, this specification is simple. So I just have 1-2 specifications, or if you want, you can say 3 specifications. So number 1 here, VDD, I'm specifying the supply voltage to be 3.3. So for you, your specification for Skywater is 1.8. Sky 130 PDK, it's 1.8. For my GF180 is 3.3. that's what you have here. So this second specification, it's the output swing. So how well I want my transistor, my amplifier to swing without having clipping. This is important for your amplifier. Oh fine, you've designed an amplifier, oh it's amplifying, nice, but you will notice some form of distortions, like because maybe as the amplifier tries to amplify, it just cuts some certain part of the signal off. Then you're not getting the complete signal, you're not hearing it as you're supposed to hear the sound. So clipping, so that happens if the output swing of the transistor, it's not that large. So output swing is it's a really good specification to look out for, because what's the point of designing an amplifier that can amplify so much, but then when the sound comes out, not like it's not amplifying, but the transistor, the amplifier itself, it's cutting off some part of the signal. Like that's like suicide, killing yourself, right? So there's no need getting rich or getting that much. So that's why I'm specifying the output swing. So you can see this is pretty large output swing. This aspect, this is the low, the minimum output swing, and this is the maximum. So this plus this, I think that's 3.1. so this transistor, so I want this amplifier, I want it to swing for a total range of 3.1. like that's really good. I mean, out of 3.3 possible voltage supply, I want to get, I hope that calculation is correct. Yes, it should be. So not 3.1, so 3.3. so yeah, 3.3. so yeah, that's my desire. So let's see if this will be granted, if the spice and every other conditions would allow this happen. But again, this is just a specification, so this is a target, we'll work towards it. second is the power dissipation. Oh, I'm looking at low power design. Oh wow, so I just want my power dissipation to be less than 700 microwatt. That's really low, really low. So let's see if this is achievable. Let's go. So just working with this. So this the you have here the topology. We've talked about this already. So for the design, what does design involve? Design, for this kind of design where I'm just giving this kind of specification, for this design, we want to be able to determine the sizing of each transistors. Most times designs involve you doing this. So when you say, oh, I'm designing, it means you want to determine one or two attributes of the transistor or features of the transistor. So sizing it, or the aspect sizing or aspect ratio of the transistor is like it is an attribute. Transistors, every MOSFET have sizings, right? So you want to determine the sizing that would enable you achieve this specification. Not only the sizing, we also want to be able to determine the bias voltage for the common source amplifier. That would also help us, achieve the specification. The third thing also we want to determine is the supply current. What should this supply current be to give us this, to help us meet these specifications? And also it's maybe the transconductance too. So but majorly those are the three things we want to determine for this design: the sizings, the bias of this M1 transistor that would help us meet this specification, and also this supply current here that would help us meet. So let's go. So I started with the power supply target. So power supply will be the total. I hope this is clear. It's seeming like it may not be. Oh shit, that's too much. Okay, so hey, no. Okay, so I'm using this formula. So the power dissipation, total power dissipation, should be I total, that's why I wrote here, times the total power supply possible, so which is just VDD, right? For a single rail power supply, VDD. So I total, so I want I total times VDD to be less than or equal to 700 microwatts, right? So I know VDD already, so that means I'm just going to be determining the I total. So I total is, at the end of the day, I total, we're saying I total should be less than or equal to that's 212, approximately 212 microampere, right? So that I total means the total current to be consumed by this structure here. So if you look at it, this structure has two arms, right? This arm here and this arm here. So we're saying the total current that should be consumed by these two arms should be less than or equal to approximately 212, and let's just say approximately, that's approximately 200 microampere, right? So I have that in mind. So again, since the sizing of this current mirrors here, it's 1:1. Remember, sizing is important for current mirrors because it determines how the current is shared between these two current mirrors, right? So 1:1, that is, I want the same current going through this transistor should go through that transistor M3, should go through transistor M2. So if the total, again, it's the total current is 200, and I want the total current, and I want equal current to flow through M3 and M2, That is, all I just need to do is to split the total current equally through M3 and M2, right? So that means, and since the current flowing through M3 is actually this I sub, this supply current, so that means this supply current would be half of the total current I desire, so which is 100 microampere. So I have determined one of those things. You remember, we're basically going to be determining about three things. So this has been determined. So that is, this is the current supply, the supply current that would help us achieve, one of our targets. You get all the specification we've done. So I move on to the next one. So given the output swing, so I want to use the output swing to determine another thing, so which is the overdrive. So I forgot to mention that. So overdrive is one of those things. The overdrive voltage is one of those things we need to determine. So from the derivation I made, I had to skip the derivation. The output swing of the maximum output swing of this M1 common source amplifier is, or of the common source amplifier, the output swing by derivation, again I skipped the derivation. It's the output swing should be less than or equal to VDD minus VOV2. That's the overdrive voltage of M2. So I know VDD 3.3, right? So all I just needed to do, and I know the output, the maximum output swing, it's given in the specification, which is 3.015, right? So I just made VOV2 the subject of formula. Then I just have this, slot in the values, and I get 0.25 volts. That's 250 millivolts. Then did the same thing for the output, minimum output swing. By derivation, the minimum output swing is given by this. Again, you have to derive to know this. It varies from different topologies. When you're talking about common source, when you're talking about let's say differential amplifier, it's all just going to be different. You get, so you have to derive it. So again, I got this to be 0.25, so that means VOV1 should be 0.25. Then with this VOV1, I'm going to determine the transconductance of each of the transistors M1, M2, M3, and I just made use of this formula, 2ID VOV1. So for GM1 it will be 2ID1 VOV1. I get this answer. For GM2 it will be GM2 and GM3. GM2, that's transistor transistor 2 and 3. They should have same, because they are all twins, right? This current mirrors like they are twins. So our desire is that their terminal characteristics should be the same thing. Then if the terminal characteristics are the same thing, so this transconductance, so terminal, I mean the current through each of them, remember it's 1:1, so they should have equal currents since it's 1:1. Then we want the overdrive to be same for 2 of them, so then it leads to their transconductance being equal also. So the same thing. Then next, you have your gain to be what? GM minus GM1, RO1, RO1, RO2, right? And RO1, RO2, they are given as this. So lambda ID1 2, and so from here I just substituted. So I want to be able to determine the gain. So what will be the gain this will give me? So I just want to determine that. So I just had to do the substitution. At the end of the day, I got the gain to be, gain is approximately 1 over VOV1 lambda, that's the channel length modulation parameter. So next I move to this. So I slotted in the values. I choose lambda to be 0. Remember, lambda is in this range. I just use lambda to be 0.24. I think it's from 0.22 sha, but I picked 0.24. So slotting this in, and I got 16 volts per volt. That will be my gain. So I'm done with that. Yeah, so next, I determine the sizing. Remember, sizing is very very important. So for the sizing, from the formula of sizing, you know the formula, the relationship between sizes and transconductance. You have this, then you just slot in all the values. All these is the model parameters, so or the process parameters been given, just slot everything in, and I got approximately this. Yeah, at the point so there may just be slight difference in values because I was trying different values, and also I hope this is the correct values I finally had to write down. So but you can just cross check. I'm sure that's it. So at the end of the day, so that means the sizing is approximately 28, or the sizing of transistor M1 is approximately 28, or you can still just leave it at 27. It all depends. You would get to know why I say it all depends. Yeah, if you're not getting what you want, you can just be moving the sizes about this. Then the same thing for the sizing for 2 and 3. You just use the same formula, slot in, and you get, I got 106 points. Yeah. Then lastly, remember you also need to determine the bias voltage for this M1 transistor. Yeah, right, the Vin. So the VGS, so you use, it's through the VGS. The Vin is basically the VGS, right? So that's, I mean, this Vin here, this large signal Vin is basically the VGS, right? So you have VGS is equal, from the formula in your textbook, you have VGS equal to V over 1 plus VT. That's the threshold voltage. So just slotting in this, then you get 0.9, and we are done with our calculation, with our design. Yeah. So next, let's just go ahead and verify our design using SPICE and see if SPICE agrees with our hand calculation. So I bring up the a scheme interface. You open your scheme and let's just get started. Let me just check the time. I'm coming. Okay, so I'm just going to stop here and continue the design. Yeah, see you in the next video.